Oh. Hey, this is Mr. A, and I'm using this really cool light board to teach a lesson on the classification of matter. So I'm going to write over here on this part of the board, which is the big things that I need to write. But you notice over here in this portion of the board over here, this is kind of a map of where you're going. So like when you're playing your video games and you're trying to figure out where the bad guys are, this is your little map over here. We're going to start right here at the very top, and we're going to work our way down. So as you're watching this video, I don't want you to sit passively and watch this video. You've got to be active. You've got to be writing. You've got to be, you have got to create this map for yourself. So don't try to get ahead. Well, you need to kind of use your paper wisely. I won't want you to scrunch everything up in one corner of the page. I want you to fill up the whole page. Leave yourself a little bit of room down at the bottom, because what I want to do on the bottom of each balloon is give you some examples of each kind of matter, okay? So again, do you need to pause the video? Whenever you need to pause the video, that's the great thing about video. You just pause the video, get out your paper, get out your pencil, start at the top, and maybe you want to write something like classification of matter. Classification of matter concept map. Anything that has mass and takes up space is matter. Matter is all around you. If you can see it, if you can feel it, it's matter. Matter is composed of atoms, and all these atoms are mashed together, and those are elements and compounds. Those are pure substances. But by and large, everything that you encounter is a mixture. You have to be in a very special place, or you have to go to a lot of trouble to get matter that is just a pure substance. All right? I'm getting a little bit ahead of myself, but just like when you're looking at your pencil, you've got lead, you've got wood, you've got your eraser, you've got metal. That's a mixture. Okay? But anything that has mass and takes up space is matter. Let me use a different pen for this. That one runs out a little bit. I like this one because it's a nice big line. All right, so starting at the top of your chart, let's split it out to begin with. Matter is either a pure substance or a mixture. Now, it's important that you put the words inside these balloons, but it's also important to the relationship from one balloon to the next. Okay? So, if something is a mixture, of course, it is going to have more than one substance. There's something else that I wanted to write there. Oh. A mixture is also more than one substance, but a mixture can be separated. A mixture, think of it like a pizza, or think of it like a bowl of nuts. On a very coarse situation, you can pull out one nut, or you can pull the pepperoni off a pizza. Obviously, that's a mixture because it has all this different stuff on it that you can separate it. If it's a pure substance, that's not so much the case, right? Because it all looks like one thing. Whenever I talk about substances, for some reason I'm always going like this, and it's like, Mr. A, what are you doing? What are you doing? Well, I always think about a talcum powder or something, some really fine powder that you kind of get on you, and it's so fine that it even gets in the little in your fingerprints, right? It's so small, and you can't distinguish the difference, but that there's anything there. It's just it's a pure substance. Okay. So this right here is the first part of our map. Okay. So now I'm going to move to what is a substance. Substance is either an element or it's a compound. All right, let's see. Maybe it's best to give you a few examples of what an element is. An element, I want to tell you, is anything that you're going to find on the periodic table. We've got a periodic table posted in the classroom. You've got a periodic table posted in the back of your textbook. But just to refresh your memory without having to stop and get out a periodic table, can you think of some things that might be on the periodic table? Like gold, lead. I want to put some really simple elements like hydrogen, oxygen, and usually, all of the elements have some symbol associated with it. So I'm going to write them here in parentheses because I am going to use those symbols in just a minute when I talk about compounds. Another one I want to use is carbon. All right, so anything that you can find on the periodic table is going to be an element. So if you have a big pile of this element, then all of the atoms of that in that pile are the same. So the relationship between substance and element is that all atoms are the same. So I have a little story, a funny story I like to say about when it's an element. If you had a big pile of stuff, and you would take and you would cut that pile in half, and then you would take the pile that you have left and you cut that pile in half. And then you take that pile that you have left and you cut that pile in half and you cut it in half and you cut it in half and you keep cutting in half until you get down to this teeniest, tiniest, smallest particle that you could have of that stuff, so that if you split it any more, it would explode, right? Because if you get down to an atom and you split an atom, the atom explodes. That's what splitting the atom is. That's what everybody was afraid that was going to happen. It was, you split the atom, it's going to blow up, right? So the atom, maybe you remember Jimmy Neutron, right? He got a little atom, he got a nucleus, and it's got this thing, right? This is what I'm talking about. Elements have, all their atoms are the same. Okay, now what is a compound? Well, a compound is more than one element, and this is key, I'm going to put quotes around it, in a fixed proportion, all right? A compound is a substance that has more than one element in a fixed proportion. So what do I mean by that? Well, let me take a compound that you're well familiar with that has more than one element. Say it's got hydrogen and oxygen, and they're in a fixed proportion such that there's always 2 hydrogen with 1 oxygen. It's a fixed proportion. If it didn't have 2 hydrogens and 1 oxygen, it would be, I don't know, peroxide or something like that. So H2O. All right, so that's a compound you're familiar with. You might be also familiar with carbon dioxide, CO2. Again, carbon and oxygen in a fixed proportion. All right, so again, it's not just that you put the names in the bubbles, you're following along writing, right? You want to write up here the relationship between a substance and a compound. It's more than one element in a fixed proportion. Okay? Make sure you list these examples because on the test I might like, you know, what is CO2? And you'd have to say, oh, it's a compound, right? All right. All right. Okay, now we are working on this part of the chart right here. Let's see, mixture, heterogeneous, homogeneous. All right, so students really get confused about this, but it shouldn't be if you know the relationships between the bubbles here. All right, so a mixture is either homogeneous or heterogeneous. I hope you understand, remember the roots of these words. Homogeneous, same, heterogeneous, different. Okay, so if the mixture has things in it that are easily distinguishable, that's a key phrase, easily distinguishable. Let me give you some examples of that. Like I mentioned before, the bowl of nuts, the pizza. There's an example in the book, though, I think I need to bring your attention to. They show a picture of somebody's shirt, and they have this magnifying glass, and they zoom into it, and it's a permanent press shirt. Now, a lot of you don't think about things like that, wrinkle-free garments and permanent press, but back in the day, it was really a revolution that you could take a shirt, wad it up on the floor, and then pick it up and put it back on, and it didn't look like it had any wrinkles in it. What caused it to do that? They actually took fibers that were, think of it like a little metal spring, and they wove the spring through the natural, say if it was a cotton shirt, through the natural cotton fibers. You couldn't see it, it was really small, the color of it blended in with the color of the shirt, but when you wadded it up, yes, the spring bent a little bit, but when you unwadded it, the spring kind of sprung back out, and it caused the fabric to go back flat again. That's what permanent press or wrinkle-free fabrics are. Why am I telling you all this? Because it comes up later on a test, right? So the point is that you really can't see it unless you look really closely, but when you do look really closely, you can easily distinguish that, hey, there's a little metal fiber in all these other cotton fibers, right? Now, homogeneous, it's really harder to tell. Let me give you an example of that. But what we want to say here is that it's evenly blended throughout. All right, let's think about that for a minute. Something like, I love to use the example of Coca-Cola, because, yeah, Coca-Cola. The first taste of Coca-Cola tastes good, the last taste of Coca-Cola tastes good. Coca-Cola Bottling Company works really hard to make sure that the flavor of Coca-Cola is uniform throughout, evenly blended throughout. So the first taste tastes like the last taste, right? So in Coca-Cola, you've got a lot of things. Well, it's mostly water, and it's got some fizz from CO2, which is a compound, and then it's got the secret formula, right? And then some caramel coloring and things like that. Well, they want to make sure the fizz and the coloring and the taste is all the same throughout. So Coca-Cola is my #1 go-to example for what a homogeneous solution is. But it could also be like an alloy, like I don't know, steel or brass, where you have different metals that you blend together to have certain properties. That's a good example. All right, so let's put some more information up here. All right. Some other good examples are granite. Like you have a kitchen tabletop or a bathroom counter, and it's got all these little flecks in it, and believe me, your mom is going to be really worried about having just the right amount of quartz and feldspar and whatever that other stuff is in granite, right? If it's big chunks, it looks one way. If it's small chunk, it looks another. I mentioned permanent press fabrics. Over here on homogeneous solutions, I mentioned metal alloys, like brass, and my favorite, Coca-Cola. Getting down to the bottom of our chart right here, we're going to talk about solutions, colloids, and suspensions. I like to mention those three things together because, well, it's kind of organized that way in your book. And this is liquid matter when we're talking about suspensions, colloids, and solutions. They are mixtures, so they're on this side of the chart over here. I included heterogeneous and homogeneous up here because suspensions and colloids are under heterogeneous mixtures, and solution is under a homogeneous mixture. So if we don't branch here, then this is just another way of saying, AKA, a homogeneous mixture is also called a solution, right? I'm just going to write also known as, AKA, a homogeneous, when the homogeneous mixture is a liquid, then it's also known as a solution. And the example that I used in this case was Coca-Cola. All right? But there are some other examples like salt water. All right, again, the requirement for a homogeneous solution is that it's evenly mixed throughout, and it's really, really hard to see the different stuff, right? If it was easy to see, then it would be a heterogeneous mixture, right? So let's talk a little bit about suspensions and colloids. Now, a suspension is kind of a misnomer because, by definition, a suspension has particles in it that are large enough that fall out. So that doesn't sound like a suspension, does it? I'm telling you this because it's kind of weird, and maybe that will help you remember that when you see the word suspension, oh, it's not really a suspension because stuff falls out of it, right? So if the particles are large enough to fall out, it's called a suspension. And the example that we have of that in my classroom is that jar of pond water that I have in the corner of my room, and it's got all the sediment in it, and some prankster every year will take that jar and shake it up, and it's like, no, no, they think they did a bad thing, when it's like, really, for the next 3 days we'll be talking about how that suspension cleared because the large particles were settling out. So pond water, river delta, you get the idea. Now, a colloid, it has smaller particles in it. The particles are so small that they don't really fall out, they just kind of float around. Let me give you a couple of examples first. Fog. Now, that's not really a liquid. I told you I was going to talk about liquid, so let's think about something else. Milk. You might have to do a little more explaining there. But fog or smoke. I think this helps when I talk about fog or smoke. That helps because you know how you're driving at night and your headlights are piercing the fog and you can see the beam of the light going through the fog. The fog doesn't just fall out like rain, right? The fog just kind of floats around because the particles are so small, they're just kind of floating up and around. Smoke is the same kind of thing. Now, milk, you might have to think about that for a minute. But if you take a glass of water and then you take and you put just a few drops of milk in it, and the milk will kind of disperse, and they'll be like all throughout. The milk won't settle down to the bottom. It'll just make your water look a little milky, right? The cool thing about that is that now you can pretend like it's fog and you can shine a light beam in it, and you can actually see the beam of light going through the watered down glass of milk. Shining the light through the solution is actually a test, which it's a test for a colloid, and the effect of the scattered light has a special name, which I'm going to write here. It's called the Tyndall effect. T-Y-N. Right? So the Tyndall effect is shining like a laser through the solution, and you can see the laser beam going through the solution. So I'm going to put this in parentheses. It's not really an example of a colloid, but you use the Tyndall effect to determine if something is a colloid or not. All right? So I think that gives us some examples. Well, let's make a little. Again, it's what's important is the relationship between the bubbles. So large particles on suspensions, really, really teeny, teeny, tiny microscopic particles. And somewhere in between is a colloid, but the particles are, they're really small, but they're not large enough to fall out, right? So the particles do not fall out. Okay, but really the better test for that is the Tyndall effect. Okay, I think that brings us down to the bottom of our chart, and I think that I've given you examples for each kinds of things. What more can I tell you to help you classify matter?